nuclear engineer in the first place because I'm an environmentalist. I believe that the world needs nuclear power, alongside solar, hydro, wind, geothermal, if we want to have any hope of moving away from the devastating environmental consequences of fossil fuels, of coal in particular. This is what drove it home for me. This photo shows the air pollution caused by coal power in Beijing. It's just one of the consequences of getting your power from the wrong source. On a bad day, just breathing the air outside is equivalent to smoking 2 packs of cigarettes, and you can feel it in your lungs. I remember traveling to China with my family in the late 1990s and seeing firsthand the coal soot and ash accumulated thick on buildings, and I had never seen anything like it before in my life. Now, in a carbon-free grid, solar and wind power are a fairly easy sell. But then, how do you approach incorporating nuclear, which is a form of power generation with a tremendous amount of baggage and some catastrophic failures? There are issues with safety and waste and proliferation and cost, as well as substantial public opposition in many countries. What I'm going to be talking about today is how all of this is changing quite rapidly for the better. Through a combination of exceptionally innovative new technologies with deep historical roots, coupled with thoughtful public outreach and really listening to people, we're now on the cusp of a new generation of nuclear reactors that I believe will be leading the way in moving the world towards a carbon-free future. I truly believe that these new types of nuclear reactors can help save the world. I feel exceptionally lucky to be part of the movement that's making this happen. So I was previously the CEO of one of the world's first advanced reactor design startups, and I also have a PhD in nuclear engineering from MIT. And right now, I'm co-founder of a new company that's designing equipment to make nuclear safer for both people and the environment. So I'll be talking today about how all of this new nuclear technology is being developed, and also its deep historical roots, and how decisions made decades ago are still echoing today. And then, most importantly, I'll be talking about what I think and hope the future here will look like. Nuclear technology began its life literally shrouded in secrecy and darkness. The majority of its early development was in conjunction with the Manhattan Project, making the bombs that were later dropped on Hiroshima and Nagasaki. This up here is one of the billboards that was outside the Manhattan Project headquarters in Oak Ridge, Tennessee in 1943. Secrecy was absolutely paramount, and many of the scientists working on the Manhattan Project later on came to deeply regret that their work was being used for nuclear research and nuclear weapons. After the war, these same scientists decided that they wanted to try and find positive, creative, peacetime applications for nuclear power. So they started developing things like nuclear-powered cars, like the Ford Nucleon shown here, and nuclear-powered airplanes, and nuclear-powered submarines. And they coupled this with a concerted effort to start explaining nuclear technology to people. They were no longer locked up in these top-secret labs, so they could get out there and start talking about the good that they hoped to achieve with this technology. This is the Atoms for Peace truck, which was built by the United States Atomic Energy Commission, the predecessor to the Department of Energy, back in the 1950s. And so this truck would travel throughout the US, going to big cities and small towns and explaining to people how nuclear works. And then, as you can see, people were literally lined up at the door trying to find out more. Walt Disney was also involved. In 1956, Disney wrote a book and accompanying animated feature called Our Friend the Atom, in which he sought to explain the science behind how nuclear reactors work, showing that ultimately they're just a fancy way of boiling water to power a turbine, while still capturing the inherent wonder that something as small as an atom could be used to produce power. So, to get into that in a little bit more detail, here's a schematic of how a conventional nuclear reactor works. So on the far left, under the containment dome, you have the reactor vessel. In your reactor vessel, you have solid uranium oxide fuel rods that are cooled and moderated with liquid water. In the vessel, they're in what's called a critical configuration. So you have a large, stable number of nuclear fission reactions that produce a great deal of heat. This heat's used to boil water into steam that turns a turbine, that drives a generator, that produces electricity. So a nuclear reactor ultimately is just a fancy way of boiling water. Back in the 50s and 60s, scientists were experimenting with new configurations of these designs. So this is also from the Oak Ridge National Lab in Tennessee, a prototype molten salt reactor that used liquid fuel instead of solid fuel and had some tremendous safety benefits associated with it. And then at the same time, scientists were also looking at reactors cooled with gas or cooled with liquid metal, this whole profusion of really, really interesting technology. And so you might be wondering, given all of the new interesting technology and enthusiasm surrounding nuclear power in the first atomic age, what ultimately caused everything to go wrong? Like, what happened here? And it turns out it is primarily the fault of submarines. So this is the USS Nautilus, which is the United States, actually the world's first nuclear-powered submarine that was commissioned in 1955. The core of this reactor is actually quite similar to that of conventional reactors today. So solid uranium fuel, cooled and moderated with liquid water. And it's a beautiful design, and it was optimized, of course, for use in a submarine, an underwater environment. Immediately after getting the nuclear submarine up and running, the United States wanted to be the first to get commercial civilian nuclear power operational. And because this was right in the middle of the Cold War, they wanted to get this done as quickly as possible, so specifically before the USSR did. And so instead of spending another decade optimizing a new type of nuclear reactor for use on land, they basically took this submarine reactor design and used it to make the world's first commercial nuclear generating station. This is the Shippingport reactor, which started operation in 1957. And so this type of reactor design, it works, and it works well. The majority of all the operating power reactors worldwide are this same type of design. But they do have one significant downside. And that's that you need a constant supply of external electric power that can continually pump water over the reactor core to keep it from heating up catastrophically. If you lose your cooling water, you end up having a meltdown. And the world has had 3 meltdowns of commercial nuclear power plants. The first was at 3 Mile Island in 1979, then at Chernobyl in 1986, and then most recently at Fukushima in 2011. I actually took this photograph myself when I visited the Fukushima site after the accident, and it was just incredibly moving and horrifying, really, just to see what happens when things go wrong. Now, it was particularly the 3 Mile Island accident that, in addition to causing a great deal of fear, it also served to stifle innovation and paradoxically locked in this older generation of conventional, traditional nuclear reactors. The sense of optimism and blue sky thinking disappeared, and the funding disappeared, and the industry hunkered down with what it had and what it knew, and it became secretive again. And that was the state of the industry for many, many decades. But now, once again, things are changing again for the better. There's now a new generation of nuclear engineers who are saying, what if we could go back to the early days of the industry and explore another path? What if we used modern technology to make things better? So what I'm particularly excited about is what's called next-generation nuclear reactors, or advanced reactors. So these are designs that use different types of fuels and coolants, like not the typical solid uranium oxide fuel rods cooled with water, but drawing on older technology from the earliest days of the industry. Things like the molten salt reactor from the Oak Ridge National Lab. I'm going to linger on molten salt reactors for a little bit longer. They're very close to my heart because that's what my previous company was working on. So here's a cross-section of what the core looks like. So in the core of a molten salt reactor, you again have a critical configuration. So stable, large number of fission reactions, generating a great deal of heat that boil water into steam. But the different thing with a molten salt reactor is that you have what's called a freeze valve at the bottom of the reactor vessel. And this is a plug of the molten salt, but electrically cooled so that it's frozen solid. And so if you have an accident where you lose off-site electric power, like a tsunami comes in and knocks out your external lines, the freeze valve loses its electric cooling, it melts, and then all of the liquid fuel drains out of the reactor core into a holding tank at the bottom. When it's in the holding tank, it's no longer in a critical configuration, so it's not generating nearly as much heat, and therefore it freezes solid on its own over the course of a few hours. So if something goes wrong, it turns into a solid. It's literally the opposite of a meltdown. And then in parallel with this, the entire system operates at atmospheric pressure, so the same pressure that's around all of us at sea level right now. And that means that there's no significant driving force that could potentially push radioactive material out beyond the site boundary. So this is in contrast to the 100 times atmospheric pressure of some traditional reactors. So even if you lose your external electricity, even if there aren't any operators on site, the reactor is able to coast gradually down to a safe stop. Right now, there are about 100 different companies worldwide that are working on different types of advanced reactor designs, including molten salt reactors. And they've collectively raised about $2.6 billion in private financing over the past 6 years. So it's ramping up incredibly quickly. And something that I've always found is quite nice is that there's bipartisan support for this. So even in this exceptionally divisive political environment, it's something that both sides of the aisle are able to agree on, such as this one particular bill that was passed unanimously, and I was lucky enough to be able to give congressional testimony in support of that work. So things are progressing incredibly quickly. There are environmentalists who are coming on board, there are sites being selected, and additional government funding is ramping up in order to safely test and deploy these plants. And so now, about a year ago, in the midst of the pandemic, I started thinking about what else I could be doing to help make this vision a reality. And so I decided to go back into the lab. I believe very strongly that the original sin of the nuclear industry is secrecy and isolationism and being closed off from the public. And the flip side of this is that people are rightly concerned about things that they can't see and don't understand, like radiation. And so what I want to do is help make the invisible visible. I started a new company that's making radiation detectors and imagers that can identify and visualize nuclear material. This photo shows my co-founder, Matt, and our first hire, Lily, in our laboratory outside of Boston. By helping people see radiation, you can help people understand radiation. It's really turning the lights back on and giving people a sense of ownership of the radiation that's all around them. Our technology can be used for environmental monitoring in and around nuclear facilities, so you can make sure that they're operating in a way that's safe for both people and the environment. And this, in turn, will allow the faster, safer rollout of advanced reactors worldwide. And we can also do cargo scanning to prevent the illegal smuggling of nuclear materials, so you're increasing the security and proliferation resistance of both the new generation of plants and the previous fleet. And there's still so much more that needs to be done. It's massively multidisciplinary, which is one of the many reasons why I love it. It's science and engineering and law and public policy and outreach. The future is uncertain, but I believe it's a time of great optimism and opportunity as we work to find sustainable and scalable and resilient ways to power our world. It's a time where we're going to need everyone's ideas and have a willingness to take calculated risks. So Let's start thinking big again and choose curiosity and communication to help make the world a better place. Thank you all so much.